So coming to dead loads, so these are a permanent category of loads that bridges have to endure for the entirety of the service or design life. The service of the self weight of the structure is usually calculated by the self weight command in the software. Like if you are designing this, or I must say rather, if you are analyzing this in the software, usually Midas, I use Midas for analysis, or sometimes StatPro. So most of you might be aware of the fact that you have a self weight command over there. So you can directly have a self weight over there. But if you are going for a manual calculation, you have to be ready with the dead load values on your own, and you have to create a certain Excel sheet which will revert back to you the exact value. So this manual, if you make the manual calculation, it would serve you as a cross reference, because many times what happens is in the software we are very happy when you get a no error file, or without a file which runs smoothly and gives you a certain value. But you cannot be sure of that value unless and until you are backed by a manual calculation, or which adds as an additional security layer for you. So it is a very good practice to manually do the calculation and then you go to the software. So so the dead load mainly depends upon the number, the type, the section geometry, the span lengths, etc., as we had previously just discussed. So like for example, if I have to calculate the dead load of the foundation, it is a very simple exercise. I just need the cross-section area, the height, the density, and I have the dead load with me. So the problem does not lie with the dead load of the foundation or the pier, which is quite simple. It lies in knowing which dead load which would actually actuate into movement. All right. So basically, for every footing that we have, okay, there's a table over here which indicates that there's a pier number 177, as we had discussed. It is at a chain 86548, and the ground level is this, and the founding level is this. So this basically tells us where the ground level starts and where the founding level is. On that lithology profile, you will also get some other levels like water table level and other levels. So over here you see A, B, C, D. There are 4 points. This is basically to reference it as per coordinates. So every footing that you see, they'll have easting and northing points, which will help them to actuate or place them on a coordinate system. And for the sake of the discussion, we are only assuming that it is going to be a concentric footing. We can have eccentric footings, but for bridge piers, eccentric footing is best avoided. That eccentric footings, you can say it is as good as not used, but it is best avoided. So how do we calculate the dead load of the piers? Like there are different pier shapes. If you have seen around, if you've gone around different cities, you'll see that every different bridge project or every different metro project will have a certain type of a pier section. Some of them would have rectangular piers. Some of them would have sections which are circular. Some of them oval. It basically depends upon the aesthetical requirement, and like it would not make a very big difference if it is rectangular or it is chiseled at the ends. But the main thing over here is many times the appeal, the construction ease, and often the availability of shuttering and some other factors. So if you have the section, it is as simple as knowing the cross section, knowing the height, you get the volume, and then you multiply to the density. Additionally, you need to know the density, as well as you need to know at what point you are cutting off the pier, as we are just discussed, because from that point on, you need to have the dead weight of the pier cap. All right. So as I was discussing, we've got different types of pier sections. So all these barriers have to be taken into consideration. And as I was discussing in one of the slides, you have to know which part of the dead load will actually incur a moment. So as far as these piers are concerned, there is going to be no moment from these piers. Okay, so only when you're going to consider the pier cap, the dead load, these portions, the outer cantilevered portions, only these portions would impart a moment upon the foundation. Yeah. So this is one of the sketches I made for pier caps. This is typical flanged four-bearing single seismic arrestor rectangular section pier cap. So basically, it is not too different from the normal pier caps. It's only that the flange portion has to be taken into consideration. And when you're calculating the load of the pier cap, you have to also be sure that you're calculating the weight of the seismic arresters, which is over here, and the bearings, right? So because this dead load is going to impart a moment on the face of the pier. Okay. So if you see, it's like a lever arm is up to the center of the pier cap. So basically you can assume that if you have a horizontal force, it is going to have a lever arm which is up till the centroid. But if there's any other load which is acting over here, which is a vertical load, the lever arm has to be until the face of the pier. When we are coming to the bridge girders, as I said, that we could have a combination of different types of girders. So we've got different types of girders. We've got concrete I section, concrete box girders, single cell, multi-cell, U girders, and other girders as well. As well as we've got steel plate girders, we've got truss girders, and a variety of combinations. So based on our requirement, we can have a different, as I had just discussed on the second slide, we can have a different girder on either side of the pier. Okay. So for this, for our understanding, we'll only have a consideration of a box girder on either side, which is a single cell box girder. All right. So how do we calculate the dead load of a box girder? If you see in the table, there are two different tables. One is for the right-hand side and another one is for the left-hand side. The part that I've mentioned over there is area for the midsection, area for the wearing section, area for the end section. So that what that basically tells me is that, yes, the part which is over here which is actually resting upon the bearings, it will have a thicker section. It will have an additional diaphragm to counter the shear forces. So the dead load from this one segment would be different from the load which is going to come from the other segments. So basically, when we're trying to have a manual calculation, we'll bifurcate the box girder into three different parts. We'll have the diaphragm section or the end section. We'll have the loads from the varying section, and then we'll have the loads from, this is the third section, it is from the midsection. So all the three types of section, they'll have a cross-sectional difference. And if you see over here, I've somewhat taken this value from an actual design report. The area of the end section, as I just discussed, since it is going to have a thick diaphragm over here, it is more. Towards the end of the section or the end of the segment, the webs would thicken because we need to have an additional provision for shear forces. So we're going to thicken the webs. Okay. And as we are going towards the center, we are going to reduce the thickness of the web. So that is why the varying section, as it is mentioned. So the varying section is that part from which is comprising of maybe 3 or 4 segments, which is actually reducing in thickness at its webs. So we'll take the average of the sectional value and we'll use that as the actual area of the varying section and the area of the midsection. If you see that we had on the right-hand side a span which was 30 meters. So I have divided the actual girder into 30 into 10, 15, and 5, which totals to 30. So what this basically tells me is that my girder is up to 10 meters of length, has a cross-sectional value of 6.5 meters square. For 15 meters, it is 7.8 meters square. And for only the end sections, I'm assuming 5 meters, it is 8.5. So based on that, I'll get the volume. From that, I'll get the density. I got the weight. So this is my total weight for the girder on the right-hand side. All right. So if I would ask you, how is this 5,600 kilonewton of weight going to act upon the pier? So if you see over here, I have not indicated it over here, but it depends upon the number of bearings. In the past pier cap slide we saw, there are 2 bearings over here. So that 5,600 has to be divided into 2 components. Okay, so half of it will be over here, maybe 2,700. Half of it will be over here. So that is how I have to divide it and distribute it. Similarly, the left-hand side, we had a span of 35 meters. So accordingly, it is divided. The cross-section is not differing. We can have the same cross-section, but we can have a longer span. We can compensate it with the design, the reinforcement, or the post-tensioning. The volume is with me. I calculated the weight. So on either sides of my pier, I got what is the weight of the box girder. All right. How it is distributed, it is depending upon my bearings. In this case, we've got 2 bearings. So 5,600 has to be divided by 2 and accordingly applied. And 6,600 has to be accordingly applied. Over here, I've only indicated the longitudinal moment. So longitudinal moment is only the total weight into the lever arm. So what is this lever arm? This lever arm is basically from that if you see over here, if my load is acting at this point, okay, from this point onwards, what is the distance up till the face of the pier? That has to be indicated in the table, which I had mentioned over here. It is 1.1 over there. I've mentioned 1 over here. So this bearing center to the pier center, this will indicate the lever arm, which has to be taken into consideration when I'm calculating the longitudinal moment. So this now gives me 5,600 into 1.1. This gives me the longitudinal movement for my section. All right. Similarly, we'll do the same for the left-hand side and we'll get the moment. So just on a small manual calculation, you found out that there's a difference of maybe 900 kilonewton. Okay. So that is that residual longitudinal movement that we were talking about.